Rotational dynamics is just a fancy way of saying that we are now going to take Newton's second law for linear motion and Newton's second law for rotation, and instead of setting them equal to 0 as we did in static equilibrium, we will allow our system to be fully dynamic, so there can be both linear and angular accelerations. To give you an example of how we can apply principles of rotational dynamics, I'd like to look at a falling yo-yo where the yo-yo is falling and I'm holding onto the string, and we're going to ask the question, what is the linear acceleration of this falling yo-yo? So we have a model of a yo-yo, which I've modeled as two disks. They have each a uniform mass and a radius, and they're connected by a cylinder. So this inner ring is a cylinder with a radius r, and the disks themselves are these outer rings, which have a radius of 2r. Now, the connecting cylinder is massless, but since our individual disks each have a mass of m, and there are two of them, then the mass of our system is going to be 2m. Of course, we're also going to need to know what the moment of inertia of our system is, and that's going to depend on which point we pick to calculate our torque about. Now, there are 2 points we could logically choose. We could choose the point where the string attaches, or we could choose the center of mass. In either case, we're going to have to know what the moment of inertia about the center of mass is, so let's go ahead and calculate that right now. There are, in this system, 2 disks, so we're going to need 2 times the moment of inertia of a disk about its center of mass. And when I go and I look at the table, or I flip over my formula sheet, I find that the moment of inertia of a disk about its center of mass is 1/2 the mass of the disk times the radius of the disk squared. So putting those things together, I get that the moment of inertia of my system about the center of mass, this is 4 times the mass of my disks times their radius squared. Or sorry, that's really not their radius, but that's the radius of the cylinder. That's this little radius squared. So we have the mass of our system as 2m, and we have the moment of inertia of our system as 4m r squared. And now that we've worked out these scalar quantities, we're ready to apply them in our dynamics equations. We're now ready to begin applying our dynamics equations. We're going to start with the one we're most familiar with. That's Newton's second law for linear motion. First, we need to say what our forces on our system are. There are 2 forces. The first one is, of course, gravity. Gravity acts through the center of mass of my system, and it has a magnitude equal to the mass of my system times the acceleration due to gravity. There's also a tension. It points upwards in the string, and that's it. Now, this equation, Newton's second law for linear motion, is a vector equation. We always want to be able to turn it into a scalar equation, and in order to do that, we're going to have to pick a coordinate system. So I will pick our regular coordinate system, where up is positive y, to the right is positive x, although that won't matter. And then counterclockwise will be my positive direction for rotation. If I draw the free body diagram of this system, it'll look something like this. I have gravity pointing downwards, and I have tension pointing upwards. And I also need then to know what my acceleration would be, because this acceleration is also a vector quantity. So I would normally expect, when I hold on to the string of a yo-yo, that the yo-yo would accelerate downwards. I also need to remember that this mass is not just mg, right? Because we have an m in our system, or in our equations. This is really the mass of my system. That's my force of gravity. And so I have to be careful when I'm writing these equations and make sure I'm including all the mass. So we've done all our setup. Now we're ready to write out our equations. I have tension, that's upwards, so it's positive. I have gravity, that's downwards, so it's negative. And that equals the mass of my system times gravity. And again, we need to be careful because this is actually mass of system equals the mass of my system times my acceleration, and it is negative. Of course, the mass of my system is 2m, and so when I write out my equations now, I get T minus 2mg equals minus 2ma. There's my equation using my variables, and we can call that equation 1. So we have one equation from linear dynamics, but we still have two unknowns. There's the acceleration of our yo-yo that's unknown and the tension in our string that's unknown. So we haven't yet solved this system. We're going to need another equation. We can now begin to look at the rotational dynamics by taking Newton's second law for rotation. As always with these rotational equations, we'll have to be careful. We have to make sure that our torque, our moment of inertia, and our angular acceleration all reference the same point when we write out our equation. Now, since we calculated our moment of inertia about the center of mass, let's go ahead and just simply use that as our location for about which we'll calculate the torque and the angular acceleration. This torque equation is still a vector equation. So as is customary, we're going to have to take this vector equation and turn it into a scalar equation by, first of all, picking a coordinate system. So I will pick our usual up being positive y, to the right being positive x, and counterclockwise being the direction of positive rotation. Now, I'd like to stick with the vector nature of torques for a moment, just to show you when I write out the net torque about the center of mass, I can always write it as a vector equation that every force will have a torque. So I'll have a torque due to gravity, and I'll have a torque due to tension. Now, depending on where I pick my axis of rotation, some of these torques could be 0, some of them might not be 0, and it all depends on which axis I choose. So since we have selected the center of mass, we can look at the line of action of each of these forces, and you can immediately see that the force of gravity has a line of action that passes through our axis of rotation. So this gravitational force will have a 0 torque, whereas this tension force will not have a 0 torque. In fact, the tension force the tension force will have a torque. Now we can calculate what that is. That is going to be our net torque about the center of mass, and we can calculate it by the equation. We just look at what is its position relative to the center of mass, the magnitude of the force, and the sine of the angle between that position vector and our force. In this case, when we look at our tension force, it is on a direct radius. So our position vector points in this direction, and the angle between them is a right angle. So this sine for the tension force is going to be sine of 90 degrees, which is equal to 1. And I get a torque due to my tension as being just now the length of my position vector, which is r, times the magnitude of my tension force, which is just T. And so the torque I get for my tension force is now just RT. That's also my net torque. So taking my equation now, I can write out my Newton's second law equation. R times T is equal to the moment of inertia about the center of mass. Well, that was what we calculated originally. So that is 4m r squared. And that's equal to then the angular acceleration about the center of mass for my system. Now, we also have to think, is this a positive angular acceleration or a negative angular acceleration? When we look at this torque, we can see that it's going to generate a torque in this direction. So the torque due to tension is going to be positive because it's in the counterclockwise direction. And as we think about this rolling about the center of mass, we're also going to see that we would expect it to roll in this same counterclockwise fashion. And so my tension is going to be, or my torque due to tension is going to be positive, and my acceleration is going to be positive. And so we can just drop those, and we get an equation that says RT equals 4m r squared alpha. And that is the alpha about the center of mass. Now, unfortunately, this introduces a third unknown. So we have our tension still unknown, our angular acceleration still unknown, and we still have our linear acceleration as an unknown. So we've got a third equation, but we have introduced a third unknown. We have a second equation, but we've introduced a third unknown. And so we're going to have to find a third equation. To get that third equation, we're going to go back to our problem statement and notice that we were looking at this yo-yo, and it said that the yo-yo rolled down the string without slipping. And that without slipping is a special condition that we need to relate the motion of the center of mass and the acceleration of the center of mass with angular acceleration about the center of mass. That rolling without slipping gives us a special equation. It says that the acceleration of the center of mass is equal to the angular acceleration about the center of mass times the distance between the point that's not slipping and my center of mass. Now for our system, the point that isn't slipping is the point where the string attaches, and the center of mass is of course the center, and so this distance is my center of mass, this distance from the center of mass to the point that's not slipping. So this is capital R. And so I get that my angular acceleration is just my acceleration, which is also then the acceleration of my center of mass, divided by this R distance. So with that, I have now three equations with three unknowns. It's a matter of substitution to solve this. I'm going to go ahead and take a moment and solve this equation 1 for my tension, and I get that the tension is equal to 2mg minus a. And now I'm going to take my rolling without slipping condition and my tension and plug them into equation 2, and I'll show you what the result looks like on the next slide. So you can see where I've plugged in my information about the tension and the information I got from rolling without slipping into my torque equation. And now it's just a matter of solving. If I look at this, I notice I have an R on this side, and I'm going to divide over here by R, and I'll get R squared. So I divide both sides by R. And of course over here that goes to 1. Here I now have an R squared over an R, so that goes to 1 as well. If I divide this by m, I can divide this by m. And if I divide this by 2, I can divide this by 2, and that goes to 2. And so I end up with an equation that says g minus a is equal to 2a. When I solve this for a, you immediately see that I get g equals 3a, or since I'm interested in the acceleration, I get that a is 1/3 the acceleration due to gravity. Now you'll notice I dropped my subscripts about the center of mass. That's because when we talked about linear equations, we were always talking about the motion of the center of mass, and so there's no ambiguity here. This is the acceleration of the center of mass, and that's what we call the acceleration of the yo-yo. So we got our result. The acceleration of our yo-yo ends up being 1/3 the rate of gravity. But let's take a moment now and think and reflect on how we got here. First, we had to just do some preliminary work. We had to figure out what the mass of our system was, these two disks together, plus we had to figure out the moment of inertia of our system because we knew we were going to need that for our dynamics equations. Once we had got that out of the way, we then began to apply what we knew of linear dynamics. You've done that before. That's good old Newton's laws. That's free body diagrams. As always, in order to take this vector equation and turn it into a scalar equation, we had to pick a coordinate system. It's best to do this explicitly. A lot of students I see do this implicitly, and they write out an equation, and they would probably have written out t minus mg equals ma. And the problem with this is that it says when I let go of the string, I'm going to get a positive acceleration, an acceleration in the same direction as my tension. So I would let this go, and I would say I'm accelerating upwards. Now, you, of course, wouldn't expect that. Nobody expects that, but that's what your math said. Your math said that my acceleration was positive. That's a problem. We want our math to reflect correct physics, and so we don't want to allow that. We want to make sure we put in our explicit minus signs. And the only way to do that is if you explicitly say what your positive and negative directions are. So we have to pick a coordinate system. Then we turned our vector equations into scalar equations. We did the same for our torque equations. And then we had to look for any other relationships we might have. This could be friction. This could be rolling without slipping, as it was in our case. Anything that will give us enough equations that we have as many equations as we have unknowns in our problem, and then we can solve our system. So that's the process for solving these dynamical systems. You'll get a chance to go over more of this in the homework, and good luck. If you have any questions, come see me.